Welcome back to the lab. Today we're going to talk about some lessons that were learned while blowing up the proof of concept inverter and changes that we want to pull forward into the next iteration of our design, in order from most to least obvious to the most casual of observer. Add stinking fuses to the inputs and outputs! More importantly, add separate fuses for the controls and power output stage, such that both circuits can be adequately protected instead of letting the whole kilowatt through and blowing up the controls. And our inverter controls can report the fault when the other rail goes dead via email or push message to alert the owner. Our original plan was way too expensive. Our 500 watt UPS architecture both wasn't going to work and was going to cost $800 per unit. Why? Well, we used line frequency magnetics, which were huge, rated for the wrong voltage, didn't have a high enough turns ratio, and cost $200 each. The battery voltage range for two cells in series will range from 30 volts to almost 14, which at the low end would have practically browned out the inverter due to losses in our lead acid batteries, and on the high end would have almost broken the inverter from giving it too much voltage. Our converter topology would have passed the 500 watts through the 4 switch mode power supplies before it got to the load, and then still needed the expensive transformer to get the job done, which is ridiculous, expensive, and inefficient. Our inverter didn't have any clamping diodes either, limiting the output voltage to the DC rail voltage, which is probably why the dielectric breakdown occurred in our primary winding of the transformer. Why? Because I didn't realize that GaN FETs don't have intrinsic body diodes the same way that traditional MOSFETs do. God! As long as we're adding circuit protection all over the place, may as well plan on adding a circuit breaker or fuse on the inverter output. Just seems like the right thing to do, eh? Whew. Now let's dive into each of those design flaws with a little more depth and describe why they are first on my list of things that need to change. Let's start with a simple one, the clamping diodes. When an inductor is designed, or a transformer for that matter, it's designed to have a maximum voltage applied across it. This drives certain design decisions, and that single parameter drives a lot of things about the physical implementation of a transformer. It can influence which type of wire insulation is used, whether windings can overlap, where windings can overlap, what kind of insulating tapes need to be used to insulate the windings from each other, whether a split bobbin is required. The list goes on. A clamping diode will cause a little bit of current to leak from the output to ground, but it would completely destroy any voltage spikes due to transient inductive weirdness and protect the transformer winding so it doesn't weld itself to itself and short out the inverter. Totally worth it. Since I'm switching to traditional N-channel MOSFETs instead of GaN FETs, some of these clamping diodes will even come for free. Score. But some of the high voltage FETs might still need external diodes. Fuses then. This was a little silly, to be honest. I went to plug in our prototype, this prototype board, into the power supply, remembering some keywords I said earlier about buying and using a current limited supply for bring-up testing. Yeah, I did it the poor man's way instead, with a resistor. That way, if excessive currents would be pulled, the circuit just rounds out instead and everything's fine. However, after I was about to remove the resistor from the circuit, I realized that there was nothing preventing like 500 watts from just cooking if we had to shoot through in the supply. And not exactly what I was looking to do with my new board. So, had to run to the hardware store and buy a bunch of inline fuse holders and inline fuses, just in case there was a short circuit condition here. Again, not great, but we got it up and running and the circuit was protected and everything was fine. But if we get some off-the-shelf fuses or PTCs and put those on the board going forward, they'll be soldered or in a fuse holder and it'll be a lot cheaper. Between the fuses that'll mitigate the hard faults plus implementing a cycle-by-cycle current limit in the inverter controller, both of those things together will greatly reduce the likelihood that our next design will suffer the same untimely end. Some tweaks to how the control loop's implemented will make this a lot easier too. The transformer size, cost, and efficiency problems all get solved in one big swoop. We're ditching the concept of a battery voltage-driven inverter stage. We're going to take the battery voltage or the DC input after the PFC up to about 250 volts DC, thereabout, and then use that to directly supply the inverter. our transformer will allow for about 600 watts to flow through it, and that's watts, not voltamps, and it will be able to support voltage regulation on the output down to about 11 volts on the input, which is good because that's right about where our battery voltage will lie when we're driving 600 watts out of them. That, in that case, if you're interested, there's about 150 watts of power dissipated in the batteries themselves. Whew, those things are going to get hot. This shift in topology eliminates the need for an output transformer, like this one, demands a separate custom output inductor, but reduces the transformer cost from around $200 for one that can handle the full power to $25. It also reduces the weight from 45 pounds to grams. Pretty sweet if you ask me. Well, I suppose 45 pounds is still something in grams. How does this all work? How do we get to wind our own transformer and reduce the cost and weight? Well, because we went from a switching frequency of 60 Hz to 100 kilohertz, which allows for much smaller and more affordable transformers to be used. In fact, that's why classic wall warts that contain a bridge rectifier and a transformer fell completely out of favor. Switch mode power supplies are the way of the future, man. I mean, they're also the way of the present, but I think you get the point. Let's talk through what the topology was and where it is now. This legacy architecture on the surface seems somewhat reasonable. Maybe you were screaming at your monitor, but I couldn't hear you, so it seemed reasonable at the time to me. However, I failed to consider the full complexity of what I was really asking for. The first issue is that we spec'd two redundant power supplies capable of handling the full output power of the system, which is a bit silly, to be honest, because we never need both supplies to be active, so we can just use one, eliminate a transformer, some high power switches, and a switch mode power supply by switching between the two DC sources before conversion to the DC bus, and then using the holdup of the bulk on that bus to keep the inverter running while we switch. Not to mention, almost nobody wants to sell a power supply with an output voltage higher than the self limit of around 50 volts depending on where you live, which means it will either need a line frequency transformer or a method to boost the DC bus voltage to something higher before it gets to the inverter output stage. The plan was originally a line frequency transformer, but that was before we understood the cost and weight of line frequency magnetics capable of handling a kilowatt. The last major issue is surrounding the so-called low-level micro. This micro is controlling things on both sides of an isolation boundary with no provisions or plan to isolate the signals or high voltage from the user, batteries, etc. This is a huge fundamental flaw, and we need to change that. How did we fix this problem? Let's dive in. To show you the larger picture, going from start to finish, here is a diagram of how the power and signals flow through our UPS. We eliminated that extra DC to DC converter, adding provisions for software circuit breaking and switching between the two low voltage supplies. This is all controlled by our low-level micro, which also manages the inverter stage, as well as enabling the DC to DC boost converter. This is critical since the DC to DC converter will soft start, bringing the common mode voltage slowly from 0 to 125 volts. This will allow the circuit breakers to open if there's an overcurrent fault due to equipment not being designed to handle common mode voltage between neutral and ground. In theory, the current here should be very small, but there's still voltage there. And since ground of the high voltage side is allowed to float, any current that's pulled should bring neutral closer to ground, but at very worst, this will be following neutral of mains with minimal current flow. However, this ramping of the common mode voltage slowly will allow for fault conditions to trip when smaller voltages and currents are at play if something does go catastrophically wrong. This will help to prevent damage to connected equipment. Temperature monitoring of the various supplies has also been added, which prevents overpower conditions from causing thermal runaway if something like a cooling fan were to break. The design now has over temperature, over current, and over voltage monitoring capability. That is huge. If any of these limits are exceeded, the low-level micro has the ability to shut everything down. Should the low-level micro lose its brains, the high-level micro is also monitoring temperature and expects a periodic ping from the low-level micro. Should this ping ever not occur, the high-level micro is able to pull the plug for that main DC boost converter and then hold the low-level micro and reset. This combination effectively disables the power stage of the UPS and makes sure that everything's safe. This will occur if a ping is ever missed or if the high-level micro detects a thermal runaway condition that the low-level micro didn't catch. The high-level micro also handles charging and cell balancing for the auxiliary DC source. We assume that these batteries will be 2 series 12-volt lead-acid batteries, which are unvented, sealed batteries. This change in architecture removes hundreds of dollars worth of components from the design, bringing the BOM cost down to approximately $300 per UPS before batteries. To put this into perspective, buying a 750 watt inverter, so that's only one DC input, no battery management, no smart interface to a PC, costs around that much. An actual double conversion UPS, like what we have built here with similar power output, runs around $550. Not bad for a DIY. Throw a couple batteries in there to achieve the runtime you desire, and the cost is almost identical for the DIY solution versus the off-the-shelf. I mean, identical except for the fact that the $550 off-the-shelf solution has a 5 amp hour battery bank, and ours will have a 100 amp hour battery bank. This should give our design approximately 1 kilowatt hour of capacity or 2-hour runtime with a load of 500 watts. This is assuming that the amp hour rating of the battery takes into account the internal losses of the battery, and our UPS has an 80% efficiency. In this case, we were able to take the power output from 500 volt amps to 700 watts and reduce the cost of the design by around $200 while we did it. Awesome! This also means that our batteries could take over 2 days to fully charge with the built-in charging circuitry, which isn't ideal, but the odds that smaller batteries will be used most of the time to save cost is pretty likely, since that's a pretty extreme runtime. The 50 amp hour batteries run $100 each. Despite some minor setbacks, we are back on a productive path for Project Darwin. We're almost ready to kick off the next phase of the project, so subscribe to be notified of our future videos, where we'll find a way to interface our inverter with Windows to shut down multiple connected computers when the runtime on the batteries gets too low. I think that this new direction is great. If you think that this new architecture will work way better than the old one, let me know by hitting the like button on this video or leaving a comment down below letting us know what you like. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EEforEveryone, and thank you for staying till the end. Bye!